Simplifying radical expressions. So what numbers are perfect squares from 1 to 100? Well, we have 1 times 1, 2 times 2, 3 times 3, 4 times 4 is 16, 25, 36, 49, 64, 81, and 100. And all these perfect squares are going to help us simplify radical expressions. So we're going to start by trying to remove perfect square factors, and we want to always try to remove the largest perfect square factor possible. If we start with, we have negative the square root of 81, well, 81 is one of those perfect square factors. The square root of 81 is 9, and the negative sign in front of the number will make it negative 9. What if we had the square root of 32? Well, if we look at our list of perfect square factors, and 36 is too big, 36 times nothing will give us 32, and work our way down. 25 times anything give us 32? No. Working our way down the list of perfect squares, I get to 16. Well, 16 times 2 is 32. So if I break this square root of 32 down to 16 times 2, 16 is a perfect square. The square root of 16 is 4, and that gives us 4 times the square root of 2. And 2 doesn't have any perfect square factors, and that's the great thing about taking out the largest perfect square is what's left under the radical sign. And this number under the radical sign is referred to as the radicand. So this is 4, and then in the radicand we have 2. How about the square root of x to the 6? Well, we're looking for what number times itself is x to the 6. X to the third times x to the third is x to the 6. So the square root of x to the 6 is x to the third. How about the square root of x squared? Well, an exponent of 2 and a square root sign are inverses of each other. They undo each other. They're like opposite operations. And we get x, or the square root of x squared is x, because x times x is x squared. How about if I have the square root of 45x to the third? Well, I'm back to my perfect square list, looking at the largest number possible. 49 is too big. That doesn't work. 36 times anything give us 45? Nope. 25 times anything give us 45? No. How about 16? Nope. 9. 9 times 5 is 45. 9 will work. And what about the variable x to the third? Well, being an odd-numbered exponent, there's not a perfect square, but x squared, just slightly below it, would give us a perfect square. So I'm going to break down the square root of 45x to the third as 9 times 5 times x squared times x. So I have two perfect squares in here. I have the square root of 9, which is 3, and the square root of x squared is x. So I take the square root of 9, I bring the 3 to the outside, and I take the square root of x squared as x, and that leaves in the radicand 5x. 5 doesn't have any perfect square factors, so I can't do anything more with that. And this x that's left, this is common. An odd-numbered exponent on a variable will leave one of the variable in the radicand. So because x squared was a perfect square, we got the x on the outside, but this x is not a perfect square, so it just remains in the radicand. Working with rationals, we don't want to have radicals in the denominator. We have a process called rationalizing the denominator, and there's an agreement in mathematics that we don't leave a radical in the denominator. That is bad. That is a no-no. We can't do that. So remember when we were in elementary school, we could use an equivalent fraction, like if we had 1/4, we could multiply by 3/3 and get 3/12, and we know that 3/12 is equivalent to 1/4. Because multiplying by 3/3 is just like multiplying by 1. It gave us an equivalent fraction. It just kind of changed the form of it. So multiplying by 1 didn't really change the value. We're going to use this same rule, but with radicals. So let's say I have 1 over the square root of 3. We can multiply the numerator and denominator both by radical 3, because radical 3 divided by radical 3 is anything divided by itself is 1. So I'm not really changing the value of it, but I can change the form to help get this radical out of the denominator. So on the top, easy. Anything times 1 is itself, so I can just get radical 3. On the bottom, the square root of 3 times the square root of 3 is the square root of 9, and the square root of 9 is 3. So that accomplished my goal of rationalizing the denominator, getting that radical out of the denominator. What if I had 4 over the square root of 2? Well, I can multiply the top and bottom by radical 2 over radical 2. 2 times 2 is 4, and the square root of 4 is 2. On the top, I'm just going to have 4 times radical 2. Now, back when we did fractions, we could always reduce fractions, and since 4 and 2 are both divisible by 2, I could divide the top by 2, and I could divide the bottom by 2 to reduce the fraction. And I just get 2 over radical 2 over 1, which is just the same as 2 times the square root of 2, or 2 radical 2. Now, there are some rules for working with radicals, and you probably want to write these down, and we can use these forward and backwards, like the square root of AB is equivalent to the square root of A times the square root of B. The fraction, the square root of A over B, is equivalent to the square root of A over the square root of B. And if I have the square root of A in parentheses to the nth power is equivalent to the square root of A to the nth. So there are 3 no-nos that come with simplifying radicals. I call them the no-no-nos. So the first no is the radicand may have no perfect square factors. So you want to pull out the largest perfect square factor possible. The second no-no, there can be no fractions under the radical sign. And our third no is there must be no radicals in the denominator. And that's the process we went through of rationalizing the denominator. So in order for a radical to be simplified, we have to meet those 3 criteria. The radicand may have no perfect square factors, there can be no fractions under the radical sign, and there must be no radicals in the denominator. So when we multiply radicals, numbers on the outside multiply the numbers on the inside. Numbers on the outside multiply to numbers on the outside, numbers on the inside multiply to numbers on the inside. So it's like the 2 and 5 multiply to give us 10, and in the radicand, the 3 and the 7 multiply to give us 21. So we're multiplying numbers on the outside to other numbers on the outside, multiplying numbers on the inside to other numbers on the inside. And then in this case, the square root of 21 doesn't have any perfect square factors, so it doesn't reduce any further. What if we have 1 over the square root of 5? We can do our process of rationalizing the denominator. We can multiply the top and bottom both by the square root of 5. Then 5 times 5 is 25, and the square root of 25 is 5. What if I have 2 over 3 times the square root of 3? You can rationalize the denominator by multiplying by radical 3 over radical 3. Remember, we want to multiply numbers on the outside to outside, inside to inside, so this is just 2 radical 3. 3 times 1 is 3, and 3 times 3 is 9. Now, when I take the square root of 9, and there's already a number on the outside, I need to multiply those. So the square root of 9 is 3, has to multiply to the 3 on the outside. 3 times 3 is 9. Then I want to check my final answer for my no-nos. The 2 and 9 don't reduce like a fraction, so that nothing we can do with that. There's no radicals, no perfect square factors in 3. There's no fractions under the radical sign, and there's no radical at the denominator, so this is completely simplified. What about the square root of 20 times the square root of 5? We get the square root of 100, and the square root of 100 is 10. Square root of 2 times the square root of 8 is the square root of 16. The square root of 16 is 4. Now, the square root of 20 divided by the square root, the square root of 50 divided by the square root of 2, we can make into a single fraction. And we see right away that 2 is divisible by 50. So if I make this into a single fraction, I can simply divide 50 by 2 and get the square root of 25. And the square root of 25 is one of our perfect square factors, is 5. So in this case, it makes sense to write it as a single fraction under the radical sign to reduce. All right, you guys try these real quick. We'll come back and check them. Pause the video here. All right, welcome back. This is another example that making one fraction makes sense because 27 divides evenly by 3 to give us a square root of 9. Square root of 9 is 3. 7 times the square root of 5 squared is the same as 7 radical 5 times 7 radical 5 is 49. 5 times 5 is 25, and then the square root of 25 is 5. And when I take the square root of 25 to get 5, 5 times 49 will give us 245. And I hope that helps everybody simplifying radicals. OUT spells out.